So let's start off by, let me remind you that today we have a review session. Next exam's tomorrow. The average on this quiz is a little bit lower. It was like the score between like 8 and 14. Kind of low. We're going to have another bite of the apple. We're going to look very carefully at this curve sketching. It's kind of one final concept. So here's a couple of things. I hate doing this way because I hate like giving you all some kind of algorithm or anything. We have to go through steps. But here's some things to consider. If I give you some function and I say, hey, I want to know what this looks like. Draw me a picture. That's new. Right? I mean, what number can you plug in? And this makes sense. 2. Find f prime intervals increase, decrease. This is why I asked those questions on the quizzes left. And local extreme. That's a good thing to look for. Find f double prime intervals where concave up or concave down, inflection points, and that's one points where it changes from concave up to concave down, or vice versa. This will give you kind of the gist of it, right? I mean, where it's going up, where it's going down. And then this adds a little icing to the cake. What does this curvature look like? Is it going up? Does it do like this? Or does it do something else, right? So what do I mean by applicable? For example, if you look at this function, if I actually graph this function, it doesn't make any sense to say what happens as x goes to plus or minus infinity, because in fact the biggest x can be is 2 and the smallest it can be is negative 2, because you can never have a negative thing at the parameters, right? So the domain of this function, the first question would be important for this one, right? The domain of this is x between negative 2 and positive 2, right? In 6, other slant asymptotes. By the way, you can generalize this to the wider class. We'll just worry about this. I'll have to tell you, So everybody knows what vertical asymptote is, right? You all know what vertical asymptote is. You all know what a horizontal asymptote is, right? You got a function that looks like this. Y equals 0 is a horizontal asymptote in both directions, right? Close to plus. Here's another kind of asymptote. What if this was twisted? What if you had a function that looks like this? Notice that as you get closer and closer, if you go out toward infinity, this function gets closer and closer to this line. It's not horizontal, right? But it's the same kind of spirit as this. So, the definition, we say f of x has a slant asymptote, has y equals mx plus b as a slant asymptote. And some folks call this an oblique asymptote. If either one, the limit as x goes to infinity of f of x minus the line 0, or 2, the limit as x goes to minus infinity of f of x minus. Can anybody give me, now I give you the freedom to be a smart aleck in answering this. Can anybody give me an example of a function that has a slant asymptote? So, well, you can certainly have, I can give you functions that have horizontal asymptotes and no vertical asymptotes. And I can give you functions that have vertical asymptotes and no horizontal asymptotes. Tangent x, that's a good example. It's got a lot of vertical asymptotes. But can anybody give me an example of a function that has a slant asymptote that isn't horizontal? Yeah, we'll be a smart aleck. Okay, that's a stupid example. The function is its own asymptote. Because the limit as x goes to infinity of x minus x is 0, right? In both ways. Can anybody give me an example of a function that has got a slant asymptote in one direction and a different slant asymptote in another? Another stupid example. This has slant asymptote y equals x in this structure. Y equals x in this structure. Right. Okay with that? Let me give you one stat. Now I'll give you a large class, which is have interest. Now, let me point out, let's look at the limit. Let's first one. X goes to negative f of x Uh, it's helpful to do this part of the problem. Uh, we discussed this type of problem last time. What's the first thing to do with any limit like this is to be a bonehead and just kind of play with this. As x goes to negative infinity, this is going to negative infinity, right? And what about x squared plus 1? Or the square root of x squared plus 1? Where does that go? Right. The square root of x squared plus 1 is going to infinity, right? Because the square root of x squared plus 1 is positive, right? And so this is one of those deals where what you have is you have negative infinity plus infinity, so I don't know what to do. Anybody remember how we went to tackle this? There you go. Right. The confusing part of this is this radical. Let me see if I can dig this out. Now this is algebra. So if I multiply this here, I better put 1 in the bottom. Right. So this is limit as x goes to negative infinity, x minus the square root of x squared plus 1. And in the top, I get x squared minus x squared plus 1. Now, what happens now is x goes to negative infinity. This now the numerator or denominator is a lot more unambiguous. This is becoming huge negative, huge negative. This is going to 0. So actually, I've got a decent picture of a big chunk of this function because what happens as x goes to negative infinity, it's going to 0. So the function goes something like this. Right? If you go to negative infinity, it's going to 0. Like this. And how about that? How do I know that actually has to be above the y-axis instead of below? Which is bigger? The square root of 100 or the square root of 101? Square root of 101. Everybody agree with that? That's essentially what's going on here. Take a large negative number, say negative 10. This is the square root of 101, and this is negative 10. This is a slightly positive number. Agreed? That's why I know way out here, even though it's getting close to 0, it's the y coordinate. Now, what about the other direction? The limit as x goes to infinity of this is infinity. Unambiguous, right? Because this is becoming huge positive, this is huge positive. But I can be a little bit more specific. Anybody want to guess what the slant asymptote is? So a slant asymptote, what that means is the function is very, very close to the line. So if you get very, very, very large, this is almost like the line. Anybody want to guess? This one actually has a slant. Anybody want to guess what this is? Think about very, very large values. That's x. The square root of x squared plus 1 is getting very close to a very, very large positive value of x. The square root of x plus 1 is getting very, very close to the square root of 101 is just a little bit bigger, right? The square root of 10,000 is just a little bit bigger. The square of 1,000,001 is just a slight bit bigger than 1,000. For very large values of x, this is almost equal to what? This is x, and this is almost another copy of x. This is just a little bit bigger. This is just a little bit bigger than x. So I claim y equals 2x is slant asymptote. So look at the limit as x goes to infinity of f of x minus 2x. And we're back to the same problem again, minus infinity plus infinity. This is actually 0. So I can tell you what this function looks like with a great degree of accuracy. It's got the slant asymptote y equals 2x in this direction. So let me give you a large class of functions. How about somebody describe to me what a polynomial is? What kind of function is a polynomial? It's got powers of x. It's just some power of x. X cubed plus 2x squared plus 3x plus 5. Let's call it x to the 10 plus x to the 8 plus x to the 7. That's a polynomial. A rational function is a quotient of polynomials. 1 over x, 2x squared, 2x over 3x cubed plus 7. These are all rational functions. If you ever have a rational function, let's say f of x is a x. Oh, here we'll see a, b, so we'll see. If you probably should have seen this actually in void, but maybe if n less than n, then f of x as anybody, if the degree on the top is really less than the degree on the bottom, what happens to the limit of this as x goes to infinity? If the degree of the top is smaller than the degree of the bottom, what happens to this function as x goes to infinity? So what if you have like 1 over x, or 2x squared with x cubed plus 7? 0 as horizontal asymptote. As x goes plus or minus infinity. That is to say, the limit as x goes plus or minus infinity, that backs to 0. And all you have to do is divide by the limit. You can use L'Hopital rule, but you can divide by the highest power, which you see on the bottom. What happens if you have a tie? Or if you have like what happens if the top wins? What happens? Top's bigger. Not necessarily. So actually, it's kind of interesting because this is plus or minus infinity. It depends on the signs, as like in what A is. But if n is equal to m plus 1, then slant asymptote. Let me keep it concrete. Let me make something. How about x cubed plus 2x plus 5 or plus 1 over let's, let's say 3x squared plus x plus 6. Notice this thing will have a slant asymptote. I'm gonna show it to you. I'm gonna show you how you can get it. And this trick always works. I'm gonna do some old-fashioned polynomial division. And I hope I don't regret it too much. Notice I put a 0x squared. Let's just keep my place. How many times does 3x squared go into 2x cubed? Well, I'm gonna need an x there. And that would be 3x cubed. Let's do it. How about this? 2/3 x. 2/3 x times this. This is just like dividing, like you learned in grade school or whatever. This is 2/3. So this is 2x cubed plus 2/3 x squared plus 14/3 x. Everybody follow how I did that? Just this times this, we'll subtract. So let's subtract. That's a 0. That is a minus 2/3 x squared. And that's a 6/3 minus 8/3 x. Now, how many times does 3x squared go into minus 2/3? I guess I'm going to need a minus 2/9. And let's see, does that multiply right? That's going to be minus 2/3 x squared. That's going to be minus 2/9 x. And that's going to be minus 14. and I subtract 1 last time. This minus this, 0. That's what I wanted. This is like minus 24 ninths minus 10 ninths is going to be minus 22 ninths x. And this is going to be 9 ninths. Now, notice at this point it doesn't divide anymore because the power x squared does not go into a single x. Everybody agree with that? So this is, I feel like I'm getting installed for 4th grade. I'm going to write my remainder. Minus 22 ninths x plus 23 ninths. X squared doesn't go in, so that's a true remainder. What does this mean? That means that this thing can be written as 2x cubed plus 2x plus 1 over 3x squared plus x plus 7. I can rewrite that as the quotient of 2/3 x minus 2 ninths. Plus minus 22 ninths x plus 23 ninths over 3x squared. By the way, math always comes full circle. So one way that you can verify this, if you so desire, is to, this is a fraction, put this over a common denominator, 3x squared plus x plus 7. When you do that and fiddle around with this, you should get back to where you started, right? So if you can take this and put it over that denominator by multiplying by this and figure out the new numerator, you should get back to this. Everybody okay with it? Notice that what we have, since the degree of this was 1 more than the degree of this, we've got a degree 1, a degree 0, and then this thing. Now, what's the degree of the top here? The highest power you see is the first power. The degree at the bottom is what? 2. What happens to this as x goes plus minus infinity? Bottom wins, so this is 0. So when x goes to plus or minus infinity, this thing is of little or no consequence. And that means, here's another way to read this. For large values of x, this complicated thing, this goes away and it's almost like this line. This right here is the slant asymptote. So whenever you have a rational function 1 degree higher than the bottom, then you can just read the slant asymptote. Let me point out that if instead of a 3, this was a 2, you would have slant asymptote 2/3. It would just be a horizontal asymptote. It would be slope 0 slant asymptote. If this top were 1, you would have horizontal asymptote y equals 0. When you have degree 1 bigger, you have slant asymptote 2/3 x minus 2 ninths. By the way, what would happen if the degree were 2 higher? What if that was a 4th power on the top instead of a 7th? Or instead of a 3rd? It would be positive or negative infinity. And actually, can you guess what would happen? Instead of for large values, if this were a 4 instead of a 3, for large values of x, instead of looking like a line, what are you supposed to look like? If this were a 4 and I went through this division, the only difference here would be my largest power of x 2. So you have sort of a slant parabola, right? So if this were a 4, then this piece here would be a parabola. If the large values of x, it would look like a crowd. If it was 3 bigger, it would look like a cubic, and so forth. So, right? But people often don't bother with that, and so they often just think about slant asymptotes. Okay. Any questions? Okay, so here is a problem. Let's work through this. I want to. Are there any questions? So I want to try to plow through some examples. Oh, and also don't forget the review session this afternoon, 5 o'clock. Bring questions. We'll try to get everybody up to speed for the test. So, my main theme here is I want to sketch. I want to see what this thing looks like. Now, sometimes I'll provide this to you, but actually, I want to know what this looks like, and this is in the theme of this example I just did. I'm going to rewrite this function. This is going to be useful here. How many times does x go into 4x squared? What do you got to multiply x by to get 4x squared? 4x. So this is going to be 4x squared plus 8x, right? Now, subtract this animal. So that's going to give me a 0. This is going to be x plus 18. How many times does x plus 2 go into x plus 18? Well, I got to multiply x by to get x. I'm digging on this. 1. So that's x plus 2. Leaving me 16. X doesn't fit into there anymore. Moral of the story is this thing be rewritten as 4x plus 1, which is the quotient, plus the remainder over what I divided by. Actually, there's a little bonus for this particular problem. It's easier for me to take the derivative of that second piece than the first. Although I will have to. Derivative of this is 4 minus and the second derivative is 32 over x plus 2. Okay. What's the domain of my function? My original function, that what can I plug in? It's going to be okay. Everything other than negative 2. Any guesses as to what happens at negative 2? What do you expect to be going on? I mean, you can't plug in anything for negative 2. What are you supposed to think your approach is going to be near negative 2? The denominator is. Well, it certainly is. So when you're very, very, very sticking close to negative 2, this numerator, that's going to be a minus 18 and 18. You're very close to 16 on the top, and very small, either positive or negative, depending on what side negative 2 you're going, right? I expect negative 2 to be a vertical asymptote. Because the values of the function are getting huge, positive or negative near them. Everybody agree with that? Okay. Let's analyze that front. If the derivative is 0, this means 4 minus 16 over x plus 2, 1 squared is 0. So this means that 16 over x plus 2, 1 squared is 4. And I get x plus 2, 1 squared must be equal to 4. So let me take the square roots of both sides of this. Careful, because you've got 2 square roots of 4, plus 2 and minus. And I get 2 critical numbers, x equals 0 and x equals minus 4. So if I were to analyze the first derivative, I think I should be thinking about negative 4, negative 2, and 0. Now, the only critical numbers are 0 and negative 4. The critical numbers have to be in the domain of the function. Negative 2 is not in the domain of the function because it's where the denominator is 0, but I need to report it. Right. Let me take another step. Okay. Now divide by 40. Okay, so let's check out this sucker here. What happens if you're to the left of negative 4, say something like negative 100? Well, that's going to be a huge number of squares, so it's very huge. 4 minus a small number, so that should be positive. How about between negative 4 and negative 2, something like negative 3? Well, if that's negative 3, that'd be 4 minus 16, that's negative. How about between negative 2 and 0, something like negative 1? Well, negative 1 again, that's going to be 4 minus, so no sign there. And how about something greater than 0, like 100? 4 minus again. So my function is increasing, decreasing, decreasing, increasing. This is a local what? Actually, good. Goes up and down, local max, and it occurs at minus 4, or whatever I get when I plug in minus 4 here. That's going to be minus 16 plus 1 is minus 15. And that's going to be minus 8, 7, I guess. Minus 4. Minus, what's it? Oh, no, there is no positive 2, because what we get is x plus 2 is plus or minus 2. Okay. So it's 2. What do I get plus? I took the square root of this, right? So I get x plus 2 is 2, that gives me 0. I get x plus 2 is negative 2. So let's see here. We'll put in negative 4. That gives me a negative 8. One is negative 7 minus 6 minus 4. 6. This down and up. What happens here? Oh, there. And then it occurs at 0. Whatever I get when I'm plugging 0 here, which is 9. What happens here? Well, what happens here is vertical asymptote. Let's look at second derivative. Second derivative for this particular problem, I think, will be easier to analyze. In this case, I get 32 over x plus 2, 1 cubed. And so x equals minus 2 is the only place that we need to. There are no sort of critical numbers. The second derivative, and the only thing we need to analyze is what happens when you have some of the asymptote. Minus 2. Well, this one's not too bad of an analysis to do. When I'm to the left of minus 2, say minus 100, positive over negative. And when I'm to the right of 2, let's say 0, positive over positive. So it should be concave down and concave up. And that is not an inflection point because it's not even one of the terms. This is vertical asymptote. So f of x has 4x plus 1 as slant asymptote. Right, because this piece goes away and my function works as x is very large, positive or negative. This goes away, or not goes away, but it's very close to 0. And so the function looks very much like 4x. So let me try to draw this baby. Okay, I've got a vertical asymptote of minus 2. And then at minus 4, I've got a local maximum. And it's at minus 4, minus 23. So it's way the heck down here. And let's see, 4x plus 1. And right here. I don't have a scale on this, but I'm just going to say this is y equals 4x plus 1. This should be a local max at minus 4, minus 23. Now, what happens? My function is increasing until it hits the local max, then it decreases back down to the asymptote. And it's always unhappy as it does this. It's always happy. Something like this. What happens on the other side of the vertical asymptote? On the other side, it decreases down to its local min at 0.9. So we'll say, yeah, the scale is terrible. That 1.9 should be way back up here. That's 3. Not a good scale. So everybody sees the scale is bad, right? if that is a 1, then that doesn't look like a 9. Then we'll assume that it's not there. Anyway, so the function is always concave up, so it's always smiling. It comes down off the asymptote, hits the local min, and then goes up. So this. And that will be a really good picture of what this thing looks like if I have a better scale. Everybody see how we did that? By the way, there's lots of little things when you work on these and practice these problems. There's lots of little clues that can help you out. Right? For example, notice that on the right side of the vertical asymptote, my function is always above slant asymptote. Everybody agree with that? It's always above this dotted line, right? This thing tells me that. Here's the slant asymptote. And if x is bigger than -2, this thing right here is a quotient of 2 positive numbers, right? So what this says is any y-coordinate function is the y-coordinate on the slant asymptote plus some positive thing, which means that every y-coordinate on the slant asymptote should be above the, or every y-coordinate on the function should be above the slant asymptote, right? If you're to the right of the vertical asymptote. On the other hand, notice if you're on the left side of the vertical asymptote, it's always below it, right? Again, this is what this is telling you. On the left side, when x is smaller than -2, this function is going to be negative, right? Because for a positive numerator, negative denominator. So that tells me the y-coordinate on the function is slant asymptote, take away some stuff. So it's got to be hanging below. Everybody okay with it? There's all kinds of little clues on this. Study these things. Okay. Any questions? Okay. Let's do it. Let's do it now. F of x is x to the 2x to the 2/3 minus x to the 4/3. Okay, first question out of the box. Where is this function defined? What can you plug in for x and everything's a-okay? Well, what's the domain of this function? What can I plug in that's okay? Anything, right? The domain of this function is everywhere. These are nice functions. They're practical powers of x. And since you're taking a cube root, you can do that for anything. The domain of this function should be everywhere. This function should be continuous everywhere. So unlike my previous example that I vertical asymptote, none of this. I should draw something that continuous everywhere. That's first clue. Let's take a couple of derivatives here. This is going to be 4/3 x minus 1/3 minus 4/3 x to the 1/3. So a little bit. Again, I pulled up the largest negative. I pulled up those 4/3. So it's kind of a common factor. And I pulled up the largest sort of negative power that I could. X to the minus 1/3. That would be with a 1 here and an x to the 2/3. And when we add it, let me take another derivative. That's going to be minus 4/9 x minus 4/3 plus, or minus 4/9 again, x minus 2/3, which is minus 4/9 x minus 4/3 times 1 plus x. Okay, any questions on how we got into this? So let's start with the first here. Critical numbers. Okay. So what we have is we have 4/3 x minus 1/3 times 1 minus x 2/3. Critical numbers are where this thing is either 0 or undefined, or at least points in the domain, which in this particular case is everything. So what do you see? One of the 0. Notice at 0, this thing is undefined, right? And so derivative is undefined. I'm going to kind of try to remember that, because that means when I draw this, what do you expect is going to happen on your picture when x equals 0? What kind of things can you draw for a continuous function where the derivative is undefined? You could have a vertical tangent, maybe. You could have a point, a constant. Like where it's a point. I expect there to be some kind of funny business. Okay, I don't expect it to look smooth or like a place where you get a horizontal. That took care of this factor. You've also got to set this equal to 0. All right. So on the other critical number, set this equal to 0. So I get x to the 2/3 is equal to 1. Cube both sides of this, and I get x squared as 1. So I get x equals plus or minus 1. So I get 3 critical numbers. At 0, the derivative doesn't exist. And at plus or minus 1, the derivative is 0. Might as well do a sign chart here. Take care of that immediately. Okay, so let's look back at this here. What happens if you're huge negative? Well, if you're huge negative, that's negative. And let's see, notice when I square things, it's positive. So that huge negative, that's going to be negative solution, positive. What happens if you're something like -1/2? Well, that's going to be negative. And 1/2 is, that's not the biggest one, so it's going to be positive. Negative here. What happens if you're positive half? Positive, and that's going to be positive as well. And what happens if you're very, very, very large, a million? Positive, negative. Oh, so these are all something interesting. So what do we have? We have a local max and local max here, and a local min. The local max is -1, local min is 0, -1. In the whiteboard, it should be 0. The 1, it should be 1. and also. So these were kind of good, and it's pretty easy to figure out. Black ones. How about the second derivative? Second derivative. What do we get? Minus 4/9 x minus 1/3, 1 plus x 2/3. Again, I get that we must consider x equals 0. That makes that every time. And also, so this is going to turn out plenty for us because this means x 2/3 is equal to -1. So what are the solutions to that? There aren't any real solutions because to solve this equation, well, of course, you can cube it again. The x squared is -1. No solution. That means this thing is always positive or it's always negative, right? Because there's no way it's ever 0. So it's always got to be one or the other. It's always got to be either positive or negative. I'll record this, but it's sort of a waste of time. There aren't any solutions to this. Notice this is an even power, right? Because you're taking the fourth power of some cube root. And this is always positive. And you got negative sign, but this is always negative. So this function is always sad. There's actually a bit of symmetry about this. This function has some symmetry. Anybody know what it is? Notice, if I replace x with -x, that's essentially a square and that's a square. So replacing x with -x doesn't change the function. This is an even function, like y equals x squared, y equals cosine x. It should be symmetric about the y-axis. Let's draw this. Oh, let me also point out, it's probably easier to see in this form here, that when x gets very large, this is large, and this is large negative. So it's going to negative infinity. And since this is either even powers in both directions, infinity and negative, this goes to negative. This is actually not too bad to draw. You have a local max at -1, 1. So here, a local max at -1, 1, and at 1, 1, and a local min. Now, this is always concave down, always. So this is always sad. It increases, decreases, increases, decreases. Always unhappy. So it should be something like this. Got to stay unhappy. Any questions? Notice, by the way, if you take the limit as x goes to 0 from plus side of f prime of x, this is getting very, very large positive, and this is near 1, so it's going to positive infinity. The slope of my tangent line is going to be very, very, it's going to infinity because I come in from this side, and it's going to negative infinity if I come in from the other side. Okay, any questions on So here's what. Um, okay, so this one I'm going to go ahead and give you the derivatives for. Uh, so this is one of the ones where I don't want you to mess things up. So go ahead and provide it. Now, let's discuss the function itself first. Let's max. What's the domain of this function? Close. Everybody agree we're going to have a serious problem with plus or minus two. Got a problem there. There's one more problem there. Notice the absolute value saves us a lot of trouble, right? Because remember, you can't take the log of a negative number, right? The absolute value saves you about here, right? Because you don't have to worry about negatives. Well, what you do have to worry about is zero, because you can't take the log of zero. There's one more point missing. That's zero. What are you supposed to happen? Yeah, I actually will. Well, let's see. Let's see what happens. Um, think about what happens when x goes to plus or minus two. Right? This is getting close to zero, right? The numerator is getting close to four. Right? So what's happening in this argument? It's positive because that absolute value is very, very large. What happens to the log is actually it's very, very large. It goes to zero. So the limit as x goes plus or minus two of f of x is equal to infinity. What happens to zero? No, no. You can't have horizontal asymptotes fine. What you actually can have. So let me remind you. Here's the ordinary log of x. What happens? Forget about the log thing. What happens if x is very, very close to zero? This is getting close to zero. What's inside, right? And it's always positive. It's always. What happens to the log of some blob is that blob goes to zero, positive side. I'm gonna draw a picture of this in a base, but here's what I know already. In fact, and it's going to turn out, this is most of the picture. Here's what I know. When you're getting close to zero, negative infinity. When you're getting close to 2 from either side, plus infinity. I know that already. So, and you know what? Let me ask you a question. What do you, very close to this asymptote, what do you expect the concavity? This is true. I would expect the concavity to be happy, sad, happy. Everybody agree with that? So that's another, this is kind of a clue. By the way, when you guys are getting started on this, it's easy to make mistakes early on. If you run into contradictions or if there's something like, okay, I've done something wrong, I'm gonna analyze this, tell me why you know what you're going to say. For example, if I was going to a vertical asymptote and I got a vertical asymptote up like that, and I got something that was like concave down, I would think, yeah, that's probably not going to work very well, right? It's concave down. So if you run into some kind of problem, I know it's vertical asymptote, it's going concave down like that. Tell me why you know it's probably going to work out well. As it turns out, this information tells us a great deal about the graph. But let's investigate further. The critical numbers here, and they're not really critical numbers. I need to investigate x equals 0 plus or minus 2. Because notice these all make the derivative undefined, but they're not in the domain of the original function. In fact, really what I'm doing is I'm analyzing what happens. Passes over the asymptotes. Let's see what we got. As x is very, very negative, say negative 100, that's going to be negative, positive, negative, so it should be positive. Something like -1 in that second range, it's going to be negative, negative, negative. 3 negatives is negative. Something like +1, negative, positive, negative, that's going to be positive. And something's greater than 2, like 400, negative, positive, positive. 6. So it's increasing, decreasing. So in particular, what's this? What happens here? Increasing, increasing. So what occurs here? See how people are going to treat you. It would be, but it's not. Why is it not what it's? It's vertical asymptote. So don't let this completely fool you. Under normal circumstances, you might think local max, local min, local max, right? But it's vertical asymptote, vertical asymptote, vertical asymptote. Notice that it's all coming together, right? Because what does it say? It increases, decreases, increases, decreases. And that's sort of the way I've drawn this already, right? Let's look at the second derivative. Well, you know, I've got to get 0 and plus or minus 2 again, but I also have to get solutions to this. I'll get x equals plus or minus 2 over 3, whatever that is. Two over radical 3 is less than 2. So say minus 2 over radical 3. 2 to the left of 3. Now, this looks a little bit intimidating, but sometimes it pays. Look at this. When I do the analysis of time, what can I say about that bottom? Look at the bottom of the fraction in the second derivative. What can you say about that? In particular, where's the bottom of that fraction? Right? This thing is always positive. So I can ignore that in my sign analysis, right? This is always positive. It doesn't ever change anything. The sign is completely determined by this term, right? And the 2 roots of this term came out of here. So the second derivative should be negative in between these roots. Something like 0, right? And outside of this, it should always be positive. So it is concave up, concave up, concave down, concave down, concave up, concave up. So let's draw a version of this. There's one more thing I should do. I'll make this up here. What happens to this? Actually, we get the log and the answer value. What happens to x squared over x squared plus 1 is x squared? Well, there's a couple of ways we can do this. What's the big power still on top? And how about on top? It's a tie. It should be the ratio. It should be 1. You know what? Multiply top and bottom by 1 over x squared is quite the easiest way to do it in general. But here in this particular case, what it calls me is look out, it's 2x and 2x. Wait a minute. X goes plus or minus infinity, natural log well, natural log of the absolute value of the limit as x goes plus or minus infinity of x squared over x squared minus 4, which is natural log 1, and natural log of 1. So this has horizontal asymptote, y equals 0 in both directions. Horizontal. So let me do this. Okay, let's break this down. What happens to this thing on the left side of -2? Always increasing, always happening. So and it's got the y-axis or the x-axis is horizontal asymptote. So something like now, what happens between -2 and 0? What happens in between these two asymptotes? Always decreasing. Should be infinity on this side of 2, negative infinity over here. Always decreasing, and it's concavity. It should be down here and up here. So there has to be a concavity change somewhere. And maybe the concavity change, it's hard to tell, is 2 over 3. And it should be symmetric here. On this side, between 0 and 2, it's always increasing, and the concavity changes from negative to positive somewhere along the way at 2 overriding 3. This should be a lot more symmetric. I'm not drawing. I apologize for that, but you know, it should be a mirror image. And finally, on the last bit, from 2 to infinity, it should be always decreasing off this asymptote, this horizontal asymptote, and it should always be that. There's a decent picture of that function. It should be a little. Yes, but anyway, this is a mirror. Everybody okay? Any questions? Yes. How about this? F prime of x is e to the -1 over x squared comes a derivative of this, which is 2 over x cubed. So this is right. So I'll also write this way. This is 2x cubed e minus 1 over x squared. 2x minus 3. So, and f double prime of x is -6 x minus 4 e minus 1 over x squared, do the product rule, plus 2x minus 3 times e minus 1 over x squared times 2x minus 3. Let me clean the second bit up a little bit. I'm going to pull e to the minus 1 over x squared out of it. That's going to leave me with -6x minus 4 and plus 4x minus 6. So this is going to be x minus 6 e minus 1 over x squared. That's going to be 4 minus 6x squared. Okay. Any questions on that so far? Okay, what's the domain? Everything's one. All values. There's one that's known. What can be written? What can you not find? Get what because you got a problem here. Zero. Okay, let's analyze. So let's look at the first derivative and the second derivative and see what happens to this. First derivative first. F prime is 2e minus 1 bracket squared over x cubed. So the only number here we're looking at is 0. 0 makes the numerator undefined, the 2e constants. It also makes the denominator 0. So 0's got a lot of problems here, but it's technically not a critical because it's not the domain of the function. But nonetheless, it needs to go into our analysis. Well, let me point out that the exponential of anything is always positive. So the top of this fraction is always positive. And so the sign, the SIGN, is determined by what happens in the denominator. And notice that it's negative, x is negative, and it's positive. X is positive, and so F is decreasing and then increasing. What do you think happens near 0, by the way? It's not continuous for sure, but I mean, huh. Let me figure that out. Is it vertical asymptote? A lot of stuff we've looked at before is vertical asymptote. I'm not sure. Let's think about that. So that was easy. There's no local anythings, right? I mean, there would also be a local min here with functions undefined. So, all right. So let's look at the second derivative. This is, if I clean this up a little bit, 4 minus 6x squared times e minus 1 over x squared over x to the 6th. Now here, I've got a few more numbers to pull out. X equals 0, again, is going to be problematic with this and this. But also, we get 4 minus 6x squared equals 0. And so I get x plus or minus square root of 2/3. So I've got more stuff to look at in this one. Minus square root of 2/3 plus square root. Now again, I get kind of a good break here because notice x to the 6th is always positive, and e to the 1 over minus 1 over x squared, that's always positive. Any explanation is positive. So the sign, SIGN again, is controlled completely by what happens here. In other words, in between these two groups here. So in this range here, say 0, This is going to be positive. And outside of this range, this piece is so big, this becomes negative. So I can come down, up, up, down. And these two right here are points of deflection. Because they are in the domain of the original function and there's nothing else. Okay. I know about the concavity. I know about increase, decrease. I probably need to figure out what the infinite. By the way, can somebody explain to me? So remember how I said I wonder if zero is part of the last this function. Can it be? If this function had a vertical asymptote of zero, what do I know about that vertical asymptote? It decreases to it, and then it increases often. All right. So it has to look like that. Everybody agree? What's the concavity of zero? Yeah, I don't think this can be a vertical asymptote, right? Because if it were, it would have to drop down into the pits of Hades this way, at the same time having positive concavity. That's going to be a problem. So let's see if we can do a more in-depth analysis to see what happens. Let's look first the limit as x goes to plus or minus infinity of e minus 1 over x. And this might help. I'm going to quickly sketch a picture of our old friend e to the x to see what that looks like. Okay, let's take this apart. Forget the stupid exponentials. This would take the side here. Limit as x goes plus or minus infinity, minus 1 over x squared. What's that equal to? What happens to 1 over x squared as x goes to infinity or negative? I should say negative 1 over x. And what's e to the 0? Good. So f of x has horizontal asymptote. Y equals 1 in both directions. So as you go far off to infinity, negative infinity, the y coordinate should be getting closer and closer. What about what happens if you're getting very, very close to 0? What's happening to this thing? The denominator is. Well, what about the whole shebang? Think of it this way. So forget the fact that it's squared just for a moment. What's 1 over a small number? What's 1 over a 10? One over a 10 is 10. What's 1 over 100? What's 1 over 1 over 100? 100. What's 1 over a million? Million. So this is actually getting huge as far as size goes, right? Because one on the top, bottom's kind of very small. And since you're squaring it, the x squared part is always positive, so this is actually going to be negative infinity. Do I agree with it? Now you got to be careful. If it weren't for this x squared, this limit wouldn't exist. You'd have to look at the left limit and the right limit, see what happens from one side or the other. Now, what this is telling me is it's saying that the argument of this is going to negative infinity. What happens to the exponential as your argument goes to negative infinity? It goes to good. That's kind of weird, right? Because the place where it's not continuous, it's actually getting closer and closer to zero. Let's draw a picture of this. Once you've got that sort of in mind, this is actually a fairly simple thing to draw. I'm going to draw this. This is the horizontal asymptote, like one. Okay, it decreases and then increases. It's undefined at this point, but it's getting close to zero. Right? It decreases and increases, and its concavity is unhappy, happy, and then unhappy. So it should look something like this. Wherever this concavity change is, that's any questions? Okay. Are you all going to be here for the review session? I hope not. If you haven't talked to me when you're done with your quiz, please do so. I mean, you don't have to, but it's an extra 10 points for you. So, um, right. So please do that afterwards. And that being said, let's do the quiz.